Today's lecture is going to have a lot of theorems and some new concepts called, we'll be defining what a compact set is and some exploring some of these things. Okay, but the first thing we are going to need is what it means for something to be, for a set to be open relative to another set. Okay, so suppose we have E, which is a subset of Y, which is a subset of your big space X. Okay, so what does it mean by E to be open relative to Y? E is open relative to Y if for every P belonging to E, if for every P belonging to E, there exists a neighborhood. Okay, let me just say, if for every P belonging to E, there exists some R greater than 0 such that Q belongs to E for every Q in Y, Q in Y such that the distance of P and Q is strictly less than E. Okay, so as an example, not example, but note, even if E is open in Y, E open in Y does not imply E open in X. E open in X, right? For example, so example, for example, look at 0, 1, which is a subset of 0, 2, which is a subset of reals. Okay, then 0, 1 is open in 0, 2, but not in R. Okay, so that gives us an example of a set which is open in a smaller subset but not in the bigger subset. Okay, theorem 2.30. Suppose Y is a subset of X. Suppose Y is a subset of X. A subset E of Y, a subset E of Y is open relative to Y, is open relative to Y if and only if E is equal to Y intersection G for some subset, for some open subset G of X. Okay, so proof with respect to the original example 0, 1, which is a subset of 0, 2, close 0, 2, you can look at 0, 1 as intersection of negative 1 to 1 open interval with R, or negative 2 to 1, or any of these things, right? So any of these things you can take as G, and then you get E as G intersection Y, right? Now, there are two sides. Suppose E is an open relative to Y. Suppose E open relative to Y. Right? Then for each P belonging to E, for every P belonging to E, there exists some RP greater than 0 such that dp comma q smaller than rp implies q belongs to E for every q belonging to 1. Right? Then let Vp be the union of all of these Rp. Let Vp is equal to set of all q belonging to Vp, q belonging to X, such that distance of P comma Q is smaller than Rp. Okay, and let G is equal to union P belonging to E Vp, and we know that it is open as it is a union of open sets. Then G is a union and union of open neighborhoods and therefore open. Okay, and we have that, and E is equal to G intersection 1. Okay, yeah, E is equal to G intersection 1 is pretty clear. For every P belonging to E, you have some neighborhood of it Vp, which is completely contained in Y, completely contained in E, and you get this as the intersection. The other way around is pretty easy. If G is open in Y, G open in X, if G open in X, and E is equal to G, and E is equal to G intersection Y, then every P has a neighborhood Vp. Then every P belonging to E has a neighborhood Vp contained in G, right? Then Vp intersection Y is contained in E, so it is open relative to Y. So E open relative to Y. So the other way direction is a lot easier, right? And this gives us a definition of what it means by being open relative to a set. Being closed relative to a set is defined similarly. Okay, and now we will get to a new definition, which is compact sets. What are compact sets? Definition. Let me define what an open cover means first. An open cover of a set E, an open cover of a set E in a metric space X, in a metric space X, is a collection of open sets, is a collection G alpha of open sets of X such that E is contained in the union or alpha of G alpha. Okay, so basically these open sets should cover the entirety of E. Right? The definition, the name is more or less self-descriptive of what it should be. Okay. What is a compact set? A subset K of X, of well, since we are dealing with metric spaces, we can call it a metric space, but otherwise it can be of any topological space. We don't need it to have a metric defined on it. As long as you have open sets and closed sets, it's fine. If a metric space X is said to be compact, if for every open cover of X, if every open cover of X, not X, of K, contains a finite subcover. So, finite subcover. What does that mean? i.e., if G alpha is an open cover of X, cover of K, then there are finitely many indices. Finitely many indices alpha 1 to alpha n, such that K is a subset of G alpha 1 union union G alpha n. Okay, so you don't need all the infinitely many sets. A small finite collection of them is going to work. Okay, note clearly every finite set is compact. Every finite set is compact. Okay, because every finite set, you'll have some open set which contains the element, well, let's label the elements E1 to En. There's some open set which contains E1, there's some open set which contains E2, there's some open set which contains E3, all the way up to some open set which contains En, right? Take one of each. You don't need all of them to be distinct. Take one open set which contains E1, one which contains E2, take one of all of these, take their union. This is a finite cover. Okay, so now let us look at some properties of open compact sets which really are helpful. Okay, oops, theorem 2.33, theorem 2.33. So we just saw that if something is open relative to the bigger set, sorry, smaller set, it need not be open relative to the bigger set, right? Compact sets are behave slightly better than that. So here's the result for compact sets. Suppose K is a subset of Y, which is a subset of X, right? Then K is compact relative to X to Y, relative to Y, if and only if K isn't compact relative to X. K is compact relative to X. Okay. So what does compact relative to X or Y mean? Note, compact relative to a set X, Y. Okay, let me just say Y. Means the open cover G alpha should satisfy G alpha open in Y for every alpha. Okay, so of course this only is, we are already assuming that K has to be a subset of Y. Okay, so this does not make sense if K is not a subset of Y, but here's what the definition if K is a subset of Y, which is a subset of X, is. Okay, once again we want to show both ways. We'll first do the slightly harder direction. Suppose K is compact relative to X. Suppose K compact relative to X. Okay, then let V alpha be a collection of open sets relative to Y, and let V alpha be a collection of open sets, actually open relative to Y, such that they form an open cover of K, such that K is contained in the union over alpha of V alpha. Okay, well, by theorem 230, which we deliberately did today, we get that these open sets must be, there exists G alpha for every alpha. So for every alpha, there exists G alpha open relative to X, open relative to X, such that V alpha is equal to G alpha intersection of Y, right? And that's true for every alpha. And since K is compact relative to X, since K is compact relative to X, there exist indices. Indices. Did I spell indices before? DIC. Indices. Alpha 1 to alpha n, alpha 1 dot 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 alpha n, such that K is actually a subset of G alpha 1 union dot 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 union G alpha n. Okay, therefore K is contained in V alpha 1 union V alpha n, right? Because as K is contained in Y. Okay, therefore K is compact relative to 1. Okay, this time the other way is easier. Suppose K is compact to relative to Y. Suppose K compact relative to Y at first, and let G alpha be a collection of open sets in X which cover K, and let G alpha be a collection of open subsets of X, open subsets of X, such that K is contained in union G alpha. Union alpha, G alpha. Okay. Let V alpha is equal to Y intersection G alpha, right? Then V alpha cover K in Y, right? Therefore, as K is compact relative to Y, therefore there exists finitely many indices, finitely many indices, alpha 1 to alpha n, that looks like alpha n to alpha n, alpha 1 to alpha n, such that K is a subset of V alpha 1 union V alpha n. Well, but V alpha 1, V alpha I belongs to G alpha I for every alpha I, right? Therefore, K belongs to G alpha 1 union G alpha n, which gives a finite subcover given any cover G alpha. Therefore, K is compact in X. Okay, so unlike open or closed that you'll see, this is slightly more well behaved. It is open. You can have open sets which are not open in the big set, but compactness is preserved both ways. Okay. Then theorem 2.34. 2.34. Compact subsets of metric spaces are closed. Compact subsets of metric spaces are closed. Okay, this is an important result. Proof. Suppose K is a compact set of X. Suppose K compact in X. X will always be a metric space for me. Metric space. We will show K complement is open. Okay. Which would mean that, oh, K complement is open, so K is closed. Okay. Suppose we have P belongs to X, P belonging to X, such that P does not belong to K, so that it belongs to K complement. Okay. Now, if Q belongs to K, okay, let VQ and WQ be neighborhoods of P and Q respectively. Oops. Be neighborhoods of P and Q respectively, such that of radius 1/2 d PQ. Okay. In that case, because K is compact, since K is compact, there are finitely many points in K. There exist finitely many points, Q1 Qn belonging to K, such that K is contained in WQ1 union WQn is equal to W. Okay, none of these contain the point P, right? Because I'm deliberately choosing my my neighborhood such that P is not contained in Q. Okay, if V is equal to VQ1 intersection ... VQn, then V is a neighborhood of P is BHD of P, which does not intersect W, which does not intersect W, and hence it does not intersect K, right? Hence phi belongs to K complement, and P is an interior point of K complement. And P is an interior point, of K complement, which follows that K complement is Uh, oh. Therefore, K complement is open, implying K is closed as required. Okay, so we saw that compact subsets of metric spaces are closed, but closed sets does not imply compactness. Closed subset of a metric space need not be compact. Need not be compact. For example, if you look at negative infinity comma 2 closed, okay, this is closed in extended R. It is closed in R. Okay. However, it is not compact. But not compact. Okay. And the proof is take G alpha is equal to minus n comma 3 for n belonging to n. Okay. Then C is equal to. Then C is contained in union alpha G alpha, but not in any finite subcover. But not in any finite subcover. Okay, we will see how to write compact, what distinguishes compact sets. There should be some result, right? These seem like really nice sets. We will see what result gives us compactness, and it would be kind of dumb for us to expect that, oh, every closed set has to be compact, because otherwise we wouldn't create a special name compact. Let's be honest. Okay, so theorem 2.35. Closed subsets of compact sets are compact. Closed subsets of compact sets are compact. Okay. Proof. Suppose F belonging to K belonging to X, where F is closed, F closed, relative to X rather than just K, and K is compact, and K is compact. Okay. Well, we want to show that it is compact, right? So let V alpha be an open cover of F. Be an open cover of F. Okay. Now, if we adjoin, if F complement is adjoined to V alpha, is adjoined to V alpha, we obtain So f, okay, in X, we obtain an open cover, we obtain open cover omega of k. Okay, so F complement is open, V alpha is open, all of them together cover so their union is open, and they cover the entirety of K, right? Hence, this is an open cover of K. Hence, there's a finite subcollection. Hence, there's a finite subcollection. Subcollection, which the book calls phi of omega, such that it still covers K. Which still covers K. And if it's covering K, it's a subset of F is a subset of X, and hence it covers F. Sorry, and hence F. F is a subset of K, so if it's covering K, it covers F also. Now, when I say F complement is adjoined, I mean to the collection. So F complement union V alpha as a set covers K. Okay, if F complement is a member of the finite open cover phi, we can remove it from phi. We can remove it from phi. We can remove it from phi. Remove it from phi, and it will still cover F. And it will still cover F. Hence, that gives us a finite subcollection. This gives us a finite subcollection. This gives us a finite subcollection of VF, which covers F. Finite subcover of V alpha, which covers F, which covers F. Okay, so if I start with a bigger set which is compact, and if I take its intersection, if I take its closed subset, it's still going to be compact, right? Corollary. If F is closed and K is but if F is closed and K is compact, then F intersection K is compact. Then F intersection K is compact. Proof. Really easy. F intersection K is closed. And F intersection K belongs to K. Okay. Now, a very, very small note that you need to make is F intersection K needs to be closed in X. Okay. But it doesn't matter. F intersection K is closed and hence compact in K. Okay. If F intersection K is compact in K, then it is compact in the bigger set X by the previous by theorem 234, I think. No, 233, because it's closed in a smaller subset. It's also, oh, sorry, compact in a smaller subset implies compact in a bigger subset. You don't have to worry about it. Okay. Then theorem 2.36, which says if K alpha is a collection of compact subsets of a metric space, is a collection of compact subsets of a metric space X of a metric space X such that the intersection of every finite subcollection is non-empty, such that the intersection of every finite subcollection is non-empty, then yes, subcollection of K alpha is non-empty. Whatever. Empty. Then the total intersection K alpha is non-empty. Okay. Note, this is not true for open sets. Not true without compact. For example, G alpha is equal to 0, 1 over n. So let me say Gn is 0, 1 over n. Then every finite intersection is non-empty, but intersection Gn is equal to empty. Okay, so the compactness is an important property of this. You cannot have this result without compactness. Okay, so let us prove this. Fix a member K1 of K1 of K alpha and put G alpha is equal to K alpha complement. Okay. Assume that no point of K1 belongs to every K alpha. Assume no point of K1 belongs to every K alpha. Belongs to every K alpha. Okay. because otherwise your intersection would have that point of k alpha. Sorry, that point of k1, right? Well, what happens now? Then the sets G alpha form a open cover of k1, form open cover of k1, and hence there is a finite and hence since k1 is compact and since k1 is compact, there are finitely many indices alpha 1 to alpha n. There exists finitely many alpha 1 dot 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 alpha n such that k1 is contained in G alpha 1 union G alpha n, right? But that means, i.e., k1 is contained in k alpha 1 complement union dot 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 union k alpha n complement, i.e., k1 intersection k alpha 1 intersection dot 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 k alpha n is actually empty. Contradiction to the fact that we assumed finite intersections are non-empty. Contradicting finite intersections are non-empty. Okay, and hence there must be some element of k1 which is in every single k alpha, therefore it should be in their intersection, right? Which means that their intersection is non-zero. Corollary: if k alpha is a sequence of compact sets, if kn is a sequence of compact sets, non-empty compact sets actually, non-empty compact sets, such that kn is strictly contains, not strictly, but contains kn plus 1, then their intersection is not empty. Then I is equal to 1 to n, n is equal to 1 to infinity. N is equal to 1 to infinity. Kn is not equal to 5. Is not empty. Okay. Let us do one last theorem and stop. Okay. Actually, yeah. Theorem 2.37. If E is an infinite subset of a compact set, is an infinite subset of a compact set K, then E has a limit point in K. Then E has a limit point in K. And in proof. So there is a related definition of compactness called sequentially compact or pointwise compact. Sorry, sequentially compact, not pointwise compact. I forgot what's the other way of calling it, which is equivalent to this. And you can eventually show that both of those definitions are equal in in general cases. Okay, and it is very useful for certain things. We are not covering it right now. We'll get to it when the time comes, but just giving you an idea that such a thing exists. So if no point in of E was a limit point of if no point in K was a limit point of E, if no point of K is a limit point of E is a limit point of E, right? Then each point K, each point Q belonging to K would have a neighborhood which is distinct from E. Would have a BHD, which contains at most one point of E. Which contains at most one point of E. And the reason we are saying at most one point is, namely, Q if Q belongs to E. Okay? In that case, it is clear that no finite subcollection of VQ can cover E. In that case, no finite subcollection. I forgot to name these neighborhoods. These neighborhoods are called VQ. NBHD VQ, which contains at most one point. No finite subcollection of VQ contains E. Can cover E. Covers E. Covers E. And the same is true. And hence K, as E belongs to K. Right? Well, since we are doing it over the entire every single point of K, this is an open neighborhood, open cover of K, which has no finite subcover, contradicting compactness. Contradicting compactness of K. Okay? And hence, there has to be some point which is a limit point. Okay? So this gives us, in a way, an alternate definition of compactness, which we might see later. But let's stop here. Next time, we'll look at what is called the Hein-Borel theorem, which tells us another way of identifying compact sets. A really nice way of identifying compact sets. Okay, so I'm going to stop this one here.